So I am the science geek of the program today. I'm a Ph.D. scientist. As my daughter likes to say, my wife is the real doctor, and I'm a chicken doctor. As we go through the talk, you'll see why that's really, really apt. And so I've been doing prostate cancer research now for about 7 years. And I'm going to talk to you today a little bit about prostate cancer, a little bit about some of the stuff we're working on, some new technologies we've developed, and more broadly, our efforts throughout Alberta to really bring research into the standard of care for people living with prostate cancer. So I'm going to be talking about starting on a high note. So, you know, we live in this incredible time of amazing scientific opportunity. You know, the reason I got into cancer research is twofold. I did my PhD in biochemistry. Believe it or not, I was studying sperm from invertebrates, and I would actually go out to the ocean. We'd collect mussels, and we'd extract their sperm. Now, I don't know what we're having on for lunch today. No, this is an important fact. So if you like oysters and mussels, actually the male oysters and the male mussels are a rich source of protein from sperm because by weight, 80% sperm. So just keep that in mind when you slurp up the next one. It hasn't changed my enjoyment, but I don't know. So I'm here doing my PhD. I find that I just met this wonderful woman. She wants to be a physician. I'm the science geek, and her father very sadly develops metastatic spread kidney cancer, and we watched him very quickly decline. And really at that time, very shocked at what little was known about metastatic cancers, about cancer treatment in general. And we were pretty savvy. We got him into the Mayo Clinic for several clinical trials. But at the time, we were shocked at how little was known and really how brutal the treatments were with very little chance of improvement. And so that was really what catalyzed my passion and interest for pursuing cancer research, and I've been doing that ever since. And one of the reasons why I wanted to do cancer research is because we're working with some of these amazing tools in research in the research lab that haven't made it to the clinic yet, and just fantastic things. So we understand much more about cancer biology than we ever have. We have we've sequenced the whole human genome, and now we're able to sequence individual genomes of individual people. And now today we can sequence the genome of an individual cell in an individual person and get an idea of what's happening, really at a level that we could not have conceived of even 10 years ago. Our ability to design drugs that are very, very specific, not only for a disease, but even for a particular patient, is just really fantastic. And as I'll talk to you about today, our ability to visualize or actually see what's going on in real time is unsurpassed. And really, we're using tools, some of which I'll talk about today, and some of which I'm happy to talk about after. Nature has been an incredibly creative process that has developed a lot of the tools that we need to fight back. And in research and in medicine, we're able to utilize these tools to make a difference. So I'm going to be talking mostly about research today, but I want to start with sort of where we are today. I mean, it seems like cancer research has been a black hole of investment, and and with the implication that large pharma are involved as well. I can completely understand the feeling that we put so much effort and we've heard so much about it. Where are the improvements? Well, actually, we've made staggering improvements, and it may be difficult for someone living with a diagnosis to appreciate. Really, you are much, much better off being alive and diagnosed today than you were 50 years ago because survival rates have improved considerably. Breast cancer survival has increased by more than 50% in the last 40 years. Prostate cancer, the sort of the interest and the involvement in research has really just picked up in the last 15 to 20 years. But we are catching up as well. Survival rates have dropped or have increased by 20% over the past couple decades. So really, research has increased the numbers of survivors, and this is a good thing. So I'll just quickly sort of step back and say, okay, what is research, right? Because it can mean a lot of different things to a lot of different people. So you look up in the dictionary, systematic investigation and study in order to establish facts and reach new conclusions. Sure, that's pretty obvious. For me, it's really, let's learn new stuff about things. So it's really, you know, when you get into it, when you get into what we know about cancer, we know remarkably little, although our knowledge is increasing. So research is a systematic approach to looking at what we know, guessing about what may be, and then testing that in a way that we can make a conclusion that we can act upon. And the talk this morning was really a fantastic illustration of taking research and applying it in real life and really taking the important messages from that. So research is done by different groups of people as well. So I'm a Ph.D. scientist. I'm not a clinical scientist per se. Clinical research is done through clinical trials in hospitals, where right at the patient care level. And physicians and clinical trials personnel all have, you know, very well-organized ways of conducting this research, and often or not, but not always, with pharmaceutical companies. And that world is quite separated from people like me who do basic research. Now, we don't like to call ourselves basic researchers anymore because we're not that basic, are we? We are fundamental researchers, right? That's funny. This basic researcher bothers a lot of my colleagues. But until we take, you know, so in Canada, particularly in the United States, we have just fantastic universities, you know, fantastic PhDs with lots of creative ideas working on very esoteric but potentially important issues. And all we need to do is get these people together to do translational research in order to make an impact from all the stuff we've learned into the clinic. So I'm going to talk to you about how we're trying to do good translational research here in Alberta, and how we're trying to build a program where we can facilitate everybody getting involved in doing better translational research. So what is translational research? So very simply, the term I like to use is research with a clear line of sight to the patient. So maybe the experiment you're doing in the lab, you know, I'm doing in the lab, I'm mixing, you know, different colored reagents together and they're smoking, and, you know, I really do that every once in a while. But thinking about what is the implication for the experiment I'm doing and how that could affect patients down the line. So we'll have a new idea in the lab. Say, you know, oh my gosh, I just, you know, in the shower in the morning, I thought, man, if I just change this protein, or, you know, I had an aha moment, or apply this drug to this new application, maybe it can have an effect. So then you know, I don't do any actual lab work these days. I approach the PhDs and folks in my lab, and I say, you know, I know you're doing a lot right now, but I got this really great idea. You should really check it out. And so we spend some time in the laboratory testing the idea to see if it has legs. And if it does, then we can collaborate with our clinical colleagues and say, look, we've seen this. We've shown that it works. We've cured all the mice in our study. The mice are really happy, but let's apply it to people. And then it may be tested in clinical trials. Clinical trials, you know, they take a long time. They're very expensive. But if something makes it through and shows a demonstrated benefit, then it makes it into clinical practice. And what's really important about having a translational research team environment is that not only can you take your ideas and immediately pass them by the physician. Say, I talk to Eric and I say, hey, I got this great idea, I don't know, to use beeswax to cure cancer. And he said, well, you know, actually in the clinic, this would never work for this reason or another. So it allows us to bounce ideas off what's happening in the patients. Or maybe we have an idea to cure a disease that he never sees, right? So we want, as a lab, to be able to address research questions that are relevant for patients. And it goes both ways. So translational research teams also have the benefit of Eric coming to me and saying, look, John, you know, I have this one patient, I'm seeing an elevation of a certain protein, and I've seen it in 10 patients now, so maybe, and it seems like these patients do worse. And so we can then take a look at that and maybe get some tissue from those patients and test in the lab, you know, is that protein, is it doing something real? And maybe can we design a new drug against it, or can we use it as a new biomarker? So be able to creating a research environment and a research team that allows us to have this dialogue is really important. And to that end, I'm going to talk about a little bit at the end of my talk, as we've created this initiative in Alberta called the Alberta Prostate Cancer Research Initiative, which is just that. It's almost 200 physicians, clinical trials personnel, basic scientists, fundamental scientists, and everybody in between sort of working together toward the common goal of making an impact on prostate cancer. Okay, so I'm going to talk most about prostate cancer today, but a lot of what I'm going to say applies to other cancers as well. If you look at the numbers, prostate cancer is a big one. It's the most commonly diagnosed cancer in Canadian men, in North American men, and out of every 100 men, about 18 will be diagnosed with prostate cancer in their lifetime. But these are the ones that we're catching. So if you look at rapid autopsy studies, there's several of them out there now. There's an estimate by age 70, up to 80% of men probably have some pathologically confirmed prostate cancer in their prostate. And clearly, these men can live the rest of their lives without having any problems. So they can live a full life living with prostate cancer. So what's really the issue is who dies of prostate cancer. And if you look at 100 men, about 3 men will succumb to the disease of prostate cancer. And the issue is we have some clue about who these men might be, but really out of the men who are diagnosed, we don't have a clear idea of who is most at risk of dying of prostate cancer. So this is a real issue and a real focus of what we're doing in Alberta. So I'm going to make a bold statement that isn't all that bold if you know the field. So men with prostate cancer do not die of cancer that stays in their prostate. So it's really the spread or metastasis of cancer that's the scary part. So in prostate cancer, typically will spread to the local lymph nodes. It really loves to sit in the bones and grow there. So, but it'll also go to the soft tissues. And when we think about the spread of cancer, it's really personified by the numbers. So the survival rates, so in North America, we do a great job of treating prostate cancer. We have great surgeons. We have some new great drugs on the market. And so if you're diagnosed with localized prostate cancer, you have a virtually 100% chance of being alive in 5 years. However, if you're diagnosed with metastatic or spread prostate cancer, that number goes down considerably. And like I said, in Canada and in North America, we treat prostate cancer very well, very aggressively. We have great tools, great physicians. And in many other countries, this number is below 10 or even below 5%. So our current diagnostic tools don't do a great job. They give us a hint about who may develop, who has a greater risk of developing metastatic disease, but they don't actually predict metastatic disease itself. And our current treatments are not designed to treat metastatic disease, although fortunately some of them have some activity. So I'll just quickly go the 30-second spiel about how cancer forms, just so it can frame the rest of what we're doing in the research. So cancer forms in the prostate, for instance. Your prostate epithelium are little tiny glands inside this walnut-sized organ beside your bladder. They're normally creating secretions, for the semen, and maybe they get a mutation and start growing out of control. So they grow out of control. It's called hyperplasia. They create a nodule. But it's really when they get to about 1 millimeter or 1.5 millimeters in diameter, they're growing out of control. So they're not organizing things around them. So they start to starve for oxygen and nutrients, and they send out help signals. So like, oh my gosh, I need more oxygen, I need more glucose, I need more sugar. And so when they send out these help signals, who comes to the rescue? Well, the blood vessels around respond directly to these signals, and they say, look, we got a guy in trouble here, we got to help him out. And they don't realize it's cancer. So new blood vessels start growing into this newly forming mass, and then the cells start to divide quicker because they're getting fed now. They start dividing quicker. Every time a cell divides, there's some minuscule chance they're going to develop an additional mutation. And it's these additional mutations that really are the deadliest aspect of cancer, because at some point, the cancer may develop a mutation that allows it to move. And once a cancer cell picks up and moves from where it is in the prostate epithelium and goes somewhere else, it's really in trouble. So it can get into the bloodstream and go anywhere in the body and set up shop. And at that point, it's very difficult, number one, to detect, and number two, to treat. So as a research group, we've been very interested in studying this process with the aim of hopefully one day blocking it. Now, I'll just quickly show you some of the down and dirty research that we do. So really, the workhorse of cancer research is the mouse model. And we've learned a lot about cancer and about how to treat cancer by growing human cancers in mice and then curing them. the issue, the real challenge with metastasis is that metastasis is a very dynamic thing. So if you take a tumor from a prostate cancer patient and you grow it in a mouse, and then you kill that mouse, chop up the tumor, and look at it under a microscope, you're really only getting a snapshot in time and a snapshot of geography of what's happening. So it's really easy to miss what's really important. And I'm going to illustrate it by having a little exercise that hopefully maybe you guys can contribute to. So you may remember this reference is getting a bit dated, but if you remember 2011 Stanley Cup, Vancouver lost in the final game, and all hell broke loose in Vancouver. But this image emerged sort of as a meme on the internet. Is this a passionate kiss or something in the middle of a riot? So what I'd like you to imagine here is that you're all scientists just for the next 10 minutes. And this is your data. So you have the snapshot in time, the snapshot of geography. So you see people in the background, you see the police there. There's obviously something going on there on the road. So what are your hypotheses? So based on this little bit of data you have, what could possibly be happening? So maybe this is a good Samaritan helping out a poor girl, in a riot on the road. Well, there's perhaps some data there that suggests that's not quite the whole story. So I mean, there's maybe some kissing going on. So maybe if you're a devil's advocate, maybe a glass half full kind of person, you're thinking, okay, maybe this is an opportunistic rioter stealing a kiss from an injured woman in her time of need. It's possible, but she doesn't look, she looks kind of into it, right? So maybe you could flip it the other side. They think outside the box. So maybe this is the police defending public display of affection, and they're going to protect the right of that couple to kiss in the middle of the road. It's probably not the case. I love this. There was actually, I believe it was an Edmonton blogger that posted, at least someone from Vancouver can score on the road. So one or all of these things may be true. But fortunately, so this picture went around the internet for a good week before we had more, and of course we need more information. Who is this couple? We've got his whole life story actually. I just went up and looked at it last night. And fortunately, somebody on a balcony two floors above the couple was actually filming the whole thing. So we actually get to see the video of what happened and how the circumstance happened. So here we have the riot police. They're running on the crowd. You can see the couple there right in the middle getting violently knocked down and are on the ground. The riot police are still, you guys are a threat, maybe not, I don't know. So now when you see the whole thing in video, you can get a lot more idea of what is actually happening. And so my conclusion based on this is the man is consoling his distraught girlfriend after she was violently knocked down by riot police. And it really hits home the fact that being able to watch something happen in real time gives you insight and information that you probably wouldn't get from a static image. So that's what we've been doing with cancer. We've been working for many years to develop technologies to be able to try to do the same thing for cancer and really get a better understanding of how it might spread. And I'm going to introduce something that you may not be familiar with. This is why I'm a chicken doctor. Because we found that if we studied human cancers in fertilized chicken eggs, we can get the most incredible information from them. So luckily, one of the reasons I came here, University of Alberta has a farm, and they produce tons of chickens and tons of fertilized eggs. And if you take a fertilized chicken egg, so this is, it's got a little baby chicken growing inside it. Normally, so it'll grow in there for about 21 days before it hatches. And it grows this membrane called the chorioallantoic membrane. It's basically a blood vessel-rich membrane that's just on the inside surface of the shell, and it uses it to get oxygen. Now, if you take these eggs and you crack them in a dish, so you get the yolk and you have the albumin, and in the middle you have the embryo growing, and on the top surface you get this very thin, transparent, full of blood vessels membrane that has been used for 100 years for studying different drugs, but up until this point, not really used for studying human cancer metastasis. So what we found is that if we take a protein from a deep sea jellyfish, it's called green fluorescent protein, so one of these beautiful jellyfish that hang out deep in the ocean, they glow green and red and all these different things. If we take that protein and put it into human cancer cells, prostate, breast cancer, colon cancer, we've done hundreds and hundreds of cancer cell lines, so we can see them. and then we microinject them into this membrane, we can actually recapitulate or reform all of the steps of cancer growth and metastasis. And what I'm showing you here at the bottom is we've taken a nanoparticle that we developed to label the blood vessels. So in red, you got all the blood vessels around the tumor. We've microinjected about maybe 150 cells, so there's little green blobs, or each little spot is a human cancer cell. And if you look at the bottom panels, you can see that after 24 hours, there's a lot of stuff going on. This is a very dynamic environment. So you see the sort of the red bloom there in the middle. So these blood vessels are growing into these tumor cells. They're saying, help, help. The blood vessels are responding by growing in. And if you look carefully around the outside edge of that blob, you can see little green spikes. So these cells are actually actively moving and invading into this new environment, which is exactly what cancer cells do when they metastasize. So we thought, this is a great model for us to grow human cancer cells and take pictures of them. So what if we develop an incubation system that allows us to keep these guys growing and happy under, a very sophisticated microscope? Maybe we can see what's happening over time, or take much more detailed images of the cancer than we've ever been able to before. So we developed some technology that allowed us to keep these chicken embryos with human cancer growing in them on the microscope for not just hours, but days. And the images we got were just amazing. So now we can look at, I'll just show this one for a second. We can zoom out and look at a whole tumor, and we can look at the cells at the edge of that tumor sort of invading into the surrounding environment and ask questions about that. We can look at individual cells that have escaped a tumor and are sitting beside blood vessels. And the most important thing is that now we can take time-lapse video and appreciate how these things happen over time. So what you're looking at here is a time-lapse video of a tumor that's very small, only about 4 millimeters in diameter. So you can see, hopefully you can appreciate, it's moving, it's dynamic, it's scary. So around this tumor you have what we call an invasive edge. So the cancer cells are moving into the surrounding tissue, taking it over. Hopefully what you appreciate is that at the very top of that green blob, so the green blob is the tumor and the blood vessels around it, and there's actually a stream of little cancer cells, maybe only a dozen, really, making headway out of that tumor. So if you're a surgeon and you do some imaging or you palpate the tumor and you say, okay, I'm going to draw a nice safe margin around it, and you can do surgery to cut it out, you'll never see those half dozen cancer cells that have made it outside of your periphery. And those are the ones that are most aggressive, most dangerous, most resistant to treatment, that come back in 5 to 10 years and are very dangerous. Because this is a microscope, we can keep zooming in, and we can zoom in even farther than this. We can look at micrometastatic disease. So this is, little, cancer cell has moved away, sitting in the bone. It's divided into about 100 or 200 cells, and it's growing. And it's, as you can see, there's a lot of movement. There's a lot of dynamics. And we can even look at, on the right here, individual cancer cells that have escaped and are moving around the bloodstream, looking for a place to set up shop and grow metastasis. So we know, actually, in patients with large tumor, that millions of cells are actually getting away from the tumor and are circulating through the bloodstream every day. But actually, the vast majority of these cells are dying. Every once in a while, one will be able to stick to a distant organ like the bone and set up shop and develop a metastatic deposit. So we now have this fantastic model to be able to ask questions like, if I use these 5 drugs, do any of them stop this deadly process of metastasis? And we can actually even manipulate genes. Because we know the human genome, we can manipulate the individual genes in these cells and ask questions about which genes are absolutely required for these cells to successfully set up shop in a distant place. And can we develop drugs to stop that? And that's really what we've been working on for the past 10 years. So what are the key differences between those cells that survive and make it all through the steps and those cells that are just sitting in the primary tumor? I mean, you get your prostate cancer, for instance, or breast cancer. If it stays in the prostate or breast and you have surgery, it's a cure. Okay, so I'm going to take you back to this. I'm going to get a little bit sciencey for a while, but hopefully I'll be able to explain it in a way that makes sense. So this great group in Stony Brook, New York, came up with the idea of actually immunizing a mouse with cancer cells. And when you immunize something, an animal or a mouse or a person with something new, they create antibodies to try to fight it off. But we can actually use these antibodies then as tools. And this is what this experiment was based on. They took a very non-metastatic cell line. So basically cells from a patient that they could grow in a mouse. They could grow these massive tumors that never spread, ever. And what they did is from the cell line that grew tumors, they managed to find one cell, actually, they started with, that was able to spread. Just by luck, it got a mutation that allowed it to spread. And they recultured that and recultured that until they were able to develop one clone of this cell line that was able to metastasize all the time. So they have a highly metastatic, highly aggressive variant of this very tame cancer cell line. And then they put them in mice. So this is a really cool experiment. And hopefully this is as sciencey as I get today. So it's really neat. So when you immunize a mouse or a person with something, you get a huge antibody response. Most of the things on the outside of a cancer cell are not important. So you get antibodies against all the stuff that you don't care about. The stuff that you care about are usually very rare. So if you immunize a mouse against the non-metastatic or the sort of the tame cell, so the mouse produces all these antibodies, and then you use cyclophosphamide, that actually basically kills all the B cells. So B cells produce antibodies. So what you're doing is that you're tolerizing, or you're making the mouse think that that cancer cell is normal. What's important about that is then you can take the highly metastatic cancer cells and put them in the mouse, and then the mouse only creates antibodies against the very unique features of that metastatic cell line. So maybe they're only present in 0.001% abundance, so you'd never find it using any other technique. But the mouse is able, through its highly optimized biology, is able to make antibodies against these things that you would never know they even existed. And that's what we were very excited to be able to work with, is they created several antibodies, one of which had a very awesome effect. So, oh yeah, there's another data slide. Okay, but I'll just tell you what it means. When we gave cancer to chickens and we gave cancer to mice and we treated them with this one particular antibody, it completely blocked the spread. Almost 100%. It was amazing. And if you looked at pictures of the tumor now, remember I showed you those pictures of the tumor where the cells are streaming out and they're aggressive? When you had this antibody present, as we see here in the bottom panel, this tumor was smooth. None of the cells were able to invade and get away and get into blood vessels. And we really, it really hit home when we did our imaging. So we're looking at here, the gray cells are the tumor cells, and on the left here I have a single cell. So when you don't have the antibody there, you don't have this new treatment, these cells they move like crazy. So they're just like little animals. They reach out their arms, they pull themselves forward, they reorganize, they let their tail go, and they make incredible headway in a very short period. This is only 12 hours. But when we had this new antibody present, we saw a remarkably different thing. So these cells are almost completely immobilized, which was really, really cool. And if you're astute and you're looking at the image, you're like, okay, wait, that one with the little pink line there, it's moving a little more than the others. So maybe it's not 100%. So that was where the imaging really told us what was going on. So if you look at this cell here on the right, all of the cells that look like they're moving are actually trying to move very, very hard. And so this new antibody doesn't stop the ability of the cells to reach forward or move themselves, but what it does do is it prevents them from letting go. They're effectively tethered or glued by their tails. And every cell we looked at in this tumor is really trying to get away and is snapping back into its original position. And this for us was one of those aha moments that we rarely get, we hope for, but we really rarely get in science, is that we thought, there are many drug programs, pharma companies, and many scientists working on all of those proteins and genes that cause the cells to reach forward and grab and pull themselves. There are hundreds of genes involved, and the great thing about biology, and I guess the worst thing for coming up with a therapy, is that the cell, you stop one thing and it does something else, and it's still able to get around. So efforts to try to stop cells moving by hitting all the stuff at the front, has been very difficult. What we found is if we could increase the stickiness at the tail of the cell just by a bit, these cells are stuck in place and don't spread. So obviously we're excited. We published this in 2008, about 6 years ago now. We call it tumor glue. It has a very complicated, real scientific name. But basically, it functions by preventing tumor cells from detaching from their neighbors. And this is not a prostate cancer. We've done this in head and neck cancer, colon cancer, breast cancer, prostate cancer. It works in many different cancers. So we think that this approach can be utilized potentially to block metastasis in a number of different cancers. So obviously, based on this information, we've got a large research group and a huge collaborative network around the world to try to come up with a drug that will do this and move it into the clinic. But we recognize the fact that this is not an easy thing. Basic scientists, fundamental scientists like myself, we're not trained to move drugs into the clinic. And it's expensive. So we know we have to get, maybe venture capital, who knows, all that other stuff involved in order to successfully move it to the clinic. And we're moving in that direction. But we know we're realistic. We know that, even in best case scenario, we may have our first drug in the clinic, 8 years, maybe 9 years. If you look at the drugs that are coming online now, they were discovered 15, 20 years ago. So we're being realistic, although we're pushing forward with great enthusiasm. But I just want to highlight how the translational research team has taken this information and used it in a way that can potentially impact patients now. So we had a conversation with the team that basically said, if we have this antibody that recognizes something really unique about cancer cells that are likely to move, perhaps it will be useful to detect in patients if they have these features and predict which patients will develop disease that spreads. And this is a very important question, particularly for prostate cancer, because we know that we are doing a relatively or very good job of diagnosing prostate cancer, but we're doing a very relatively poor job of diagnosing those prostate or distinguishing those cancers that are likely to be deadly. So this potentially could be developed as a test to say, I think most importantly, at least in 50% of men who are diagnosed with prostate cancer, you may not need immediate treatment. And this could have a very significant effect because there is a huge gray area in intermediate risk tumors where it's up to the patient really to decide what the course of treatment will be. And obviously treatment decisions in prostate cancer come with consequences, quality of life consequences. So we believe that this test can give us the information as patients and as physicians that we really need to make these decisions more confidently. So at this point, it's just an idea. So we have the translational research team. We got to answer this question: will this antibody be able to predict metastasis like we think it might? So we actually, prostate cancer, it's a very slow developing disease. So you need patients who were diagnosed far in the past to be able to ask, in the future, did they develop metastasis? So we put together a cohort of 138 patients we got who had been treated in the last 20 years, and we asked 2 questions. Right? The first question is, so we got their tumor samples after the surgery, and we said, if they stain positive for this protein, did that predict whether they were going to develop recurrent, were they going to recur quicker? And in another subset of patients, we asked the question, if they stain positive for this in their biopsy, did they develop metastasis quicker? And I won't show you that, only that we compared this particular antibody. So there are actually there are many other antibodies against the same target that are out there. And we learned very quickly in this study that our antibody was detecting something unique. So other antibodies detected normal, prostate just fine. Our antibodies seem to be very specific for cancer. And then when we looked at patients who stained positive and negative for this antibody on their tissue, they recurred significantly earlier if they stained positive. What's more important and more useful is that it was almost completely independent of their PSA score. So it provided information over and above what PSA provides. So if they had low PSA, so below 8 after surgery, and stained negative for this antibody, none of those recurred. Consequently, if they had above 8 PSA and they stained positive for this antibody, they had a much higher chance of recurring early. Probably the most exciting but preliminary data was from the metastasis. So it's tough in prostate cancer to get enough patients to really definitively answer that metastasis question. It's something we're working on now. But basically, patients who tested positive for this with this antibody developed metastasis 10 years earlier. So a huge difference. So this provided us with the information and the confidence to move forward with a much larger study. So at this point, we have this antibody that we got from this neat experiment in mice. It detects something that's distinct from all the other antibodies that are out there. It predicts how quickly patients are going to recur after surgery and how quickly they're going to develop metastatic disease. And so we think this could be very promising to distinguish between sort of non-aggressive and aggressive cancers, and hopefully direct treatment in a way that will be useful. And obviously, this is not a prostate cancer-specific thing, so it could be used for almost any cancer. But we're left with the fact that one of the options for patients who've been diagnosed with cancer that may not want to take action immediately is active surveillance. And active surveillance requires, obviously, that you be followed over time to see if the cancer is progressing. And following over time means PSA tests, which are innocuous, but also biopsies, repeat biopsies. And we know that, obviously, biopsies are very uncomfortable. They also carry a significant risk of infection and hospitalization. And I mean, who wants to be jabbing needles into somewhere where there's cancer? I mean, it's just something you want to avoid. So we thought, because metastasis is the movement of cancer cells into the bloodstream, we thought, let's look after the prostate. So let's look in the blood, let's look in the urine to see if we can use our antibody to detect the same things there. And we actually, so the problem is the technology wasn't available to be able to do that. So what we wanted to do is take basically a liquid biopsy of the prostate. And we were fortunate, actually through a Google search, to find this guy in the UK. He's an engineer. He's another science geek. But he had a contract with the British military to create this very unassuming-looking beige box. And what he designed it for was to detect viruses in military in the field. So this thing weighs nothing. It has a bulletproof carrying case. I think it's bulletproof itself. We haven't tested that. And it's used in the field, basically with a couple drops of blood, to detect viruses to see if the military have been attacked with bioweapons. So we thought this would be perfect to look in the bloodstream for little tiny fragments of prostate cancer cells that are floating around, because cells are always dying in the prostate, and especially if they're trying to escape, there are little tiny fragments of them going around. So this would be a way for us to look at these tiny fragments and use our antibody to do the test. And again, this is data. What I want to focus your eyes on is the red box. So we put these samples in this military machine, we put our antibody in, and if the antibody sticks to the particles, then stuff in this red box lights up. And very first patient, we took one with metastatic disease and one with localized disease. Massive difference. So we got really excited about this. We ran another study with 100 patients, basically asking the simple question at this point, if you have metastatic disease, do you have a lot more of these fragments floating around? There was a huge number, a huge increase in fragments floating around. And when we looked, we unblinded ourselves. So if you took the percentage of prostate fragments floating around that actually stuck to this antibody, most patients were in the 50, so patients with localized but not metastatic disease were sort of in the 10 to 15% range. And all of our metastatic patients were all well above 40%. So a huge, this is perfect in a test because we have a huge stratification between those that are negative and those that are positive. So we're very excited about the potential for this to predict in the future. So this is just showing now at this point that we can say if you're metastatic or not. And what we hope it will do is at diagnosis, we predict that these features will already be present, and we're actively looking to answer this question right now. And this is where I'll start to talk about our Alberta Prostate Cancer Research Initiative. So basically, we can look at fragments of prostate cancer moving around in the bloodstream using this really cool machine. We can use our antibody in this test to see if we can predict metastasis in these patients with just a couple of drops of blood. And if we can use this machine for a clinical test, it's really exciting because it's non-invasive. It's just a couple drops of blood. We're looking at urine as well. Actually, we're looking at semen as well. we can look at multiple things simultaneously. So we have this one antibody. We can throw in other antibodies that people have found as well. So we're going to be trying that as well. And we can test it every week. We don't have to worry about side effects of taking blood. So this can be tested many times, and it's a very small volume. So that brings us to what are the next steps. And the next steps are not easy, as they always are when it comes to bringing things into clinical practice, because new biomarkers are discovered almost weekly. There's a new test for something. But in order to make it to the clinic, there's a very high bar. You need to do a bona fide, prospective, population-based study where you test thousands of patients to really get the answer, is this detecting what you think it is, and will it change the management of patients? So to do that, we've put together a ragtag band of physicians and other basic scientists who are interested in this stuff to create the Alberta Prostate Cancer Research Initiative. Our initial goal is the development of biomarkers to predict the outcome of prostate cancer. This is a Made in Alberta initiative. So the core group are all Albertans, but we have an international network of collaborators that are helping us work toward this common goal. Oh, and I'll just say as well, as you'll see what we're doing, we have very generous funding through the Alberta Cancer Foundation, through a really dedicated group of guys in Edmonton called the Bird Dogs for Prostate Cancer Research that really made this possible through their passion and their dedication. I really can't thank them enough. And what's really important, the reason I want to highlight that is it really drives the passion of me and our group to really follow these things up. And Prostate Cancer Canada and Alberta Innovates Health Solutions are funding a significant portion of these studies. So what is the goal of our group is to make research a part of the standard of care in Alberta and eventually beyond. So we have a plan now to actually enroll, starting last summer, almost 9,000 patients. And what this will do, so like I said, if we want to validate a new test, we need lots and lots of patients because we need very confident numbers in what we're doing. We just don't want to publish a paper that says, look, it looks like it works. We want to know it works, and we want to convince the world that it could be useful for changing management of care. So we've created a team that's now going to recruit up to 9,000 patients. And many of the team members are here. We actually have a booth outside. They're all volunteering here today to share some of the information with you about the trials. But broadly, we thought if we're creating this initiative, we don't want to just do this one thing. So the goal of the group is to facilitate prostate cancer research in Alberta. We're actively raising money. We're starting clinical studies. And what's most important, so what we found, we looked out there, we said, look, someone obviously has thought of this before. So there are biobanks out there. Australia has a big one, Montreal or Quebec has a big one, Toronto has a big one, that we can use to validate the test. One of the biggest problems we found is the clinical data. So you can have all the blood samples in the world. I can get 60,000 samples from Toronto. But if you don't have all of the clinical data in front of you to be able to put the test and get the results, it's not very useful. So this Made in Alberta biorepository and clinical registry will have all of the data live, ready for us to analyze. And it's going to be a good deal of work, and it's going to require us to work with the government and get everybody on side. But it's going to be worth it because we're going to be able to do great things. And it's going to create something state-of-the-art that's not present anywhere else in the world that other people can use to answer important questions about prostate cancer. The last thing I want to say is that we're not just talking about biomarkers. This group is, and the work we're doing is going to allow us to facilitate what we call high-content clinical trials. So trials of the newest prostate cancer drug, for instance. Typically these trials, pharma companies are getting more on board with collecting information, but really it's about taking that information and sharing it with a wider audience. So we're lending some of our expertise to help clinical trials, but also getting valuable information from that to inform our research goals. So I just came to Alberta 3 years ago. What a fantastic attitude everybody has here. It's a can-do attitude. I've been so impressed with everybody, sort of the excitement and the way we've been able to achieve so much. So members of our group in Alberta, there are about 3.7 million people that we serve through a single medical system. And the majority of prostate cancer patients go through 2 clinics in Alberta, which is you look at Toronto, there are 4 or 5 big hospitals in Toronto, all competing with each other for patients, all keeping their own data to themselves and not sharing. So we have an opportunity in Alberta. I mean, there's a little bit of rivalry between Calgary and Edmonton. Actually, my daughter came back from daycare the very first day, and she said, "Yeah, go Edmonton. Calgary sucks." I'm like, no. We don't say that out loud. Yeah, exactly. Anyway, so we haven't encountered that at all. We've got fantastic collaboration between the cities, and we're building this team out. So the demographic and clinical data is available for this large cohort of patients, and if we can get everything organized, we can put it all into a single place to be able to answer questions. What's most important is that when we have everybody part of the team and we come up with something that's actionable, we can then deploy it to the team and make province-wide changes to change clinical management in Alberta, which is exciting. And we have a unique opportunity here in Alberta to set example for other jurisdictions to cooperate. That's a complicated slide. So we have a lot of people involved. So there are basic scientists, pathologists, urologists, radiation oncologists, all of the everybody who's involved, all the way from basic science to all of the treatment, are involved in the program, and we're sort of getting new members all the time who are contributing to the team. I'll tell you a little bit about this 9,000 patients. So we're recruiting patients right now in the clinics in Calgary and Edmonton. We're in the Cross Cancer. We're in the Tom Baker. And the goal is first to recruit 2,500 patients who actually don't have a diagnosis yet. So they're suspected for prostate cancer, but they haven't received the diagnosis yet. And the goal here is to create a state-of-the-art, unique group of patients that will allow us and others to create a new diagnostic test for prostate cancer. Because we know the PSA test has issues. The PSA test was designed after surgery. So once you have your prostate out, your PSA should be 0. But before that, all bets are off. There are so many things that can raise PSA that aren't cancer. PSA, 25% of patients with positive PSA have cancer. It's only 25% specific. So we need a better test. We can't make a better test. We can't validate a better test unless we have those samples. And the remaining 6,500 patients will be to answer other questions. Can we predict response to the new drug that's on the market? Can we predict response, or can we predict which patients will do better on certain treatments? And can we predict which patients will develop aggressive metastatic disease? So to do this, we've had to create new entities. So we've created a brand new Alberta Prostate Cancer Biorepository. So we've hired professional staff. They're embedded in the clinics. They're working with the urologists, and they're all under our umbrella. And we've created a brand new registry. So we're working with the Alberta Cancer Registry. We've created this fantastic database that can be used by members of our group and others to answer important research questions, and we're super rigorous. So our standards for both collecting the samples and for collecting the data are at or above the standards of any other biobank in the world. And although I didn't personally do much of this work, there have this amazing team that have been working hard, because I don't know if you guys have been in Alberta long, but I've noticed that things seem to change in Alberta a lot. Just when we finally get something organized and everybody knows what they're doing, it completely gets turned on its head. And this is no different. The healthcare system has been, one of the worst areas for that. So the data is there, and we do collect it, but getting it all in one place has really been a challenge, and one that we're pretty much, we've launched our database now. It's live, and it's working, and we're getting data on patients, which is very exciting. So very quickly, a patient goes to the clinic, maybe coming from their family doctor, has abnormally high PSA, maybe abnormal DRE, and so when they go to the clinic, the urologist in Calgary and Edmonton will say, hey, look, you're suspected for prostate cancer. We know that you have a PSA test that's very uncertain. We don't have great information to predict whether you have cancer. If we do a biopsy, we'll have better information. But really, we want to improve the test that we can give you and the information we can give you. And so if you join our study, we're going to be able to help develop those tests that will give us more confidence. And then you're referred to one of our wonderful clinical research coordinators. Leanne Demon and team are here. You can chat with her. She's great. She's efficient. She's smooth, and she's doing a great job in making it easy for people to contribute. And we collect these. We collect a lot. We ask a lot of questions, so we know a lot about what your diet, your nutrition, your family history, et cetera, and all of this data goes together into our database that allow us to really inform the results well of our new test and other things. Okay, so I won't go into that too much, but just to say that we're not just thinking about the questions we have to ask. We're making sure that we create a resource that will be useful for years to come. So that's why we're trying to hit standards that hopefully will be useful years and years. So 5 years from now, we come up with a new way of testing blood, maybe genome sequence in 5 minutes. These samples will be available to be able to rapidly answer that question with live and important data. So last thing I want to share with you before I stop is we've just soft launched our website. So we recognize that through talks like this, I can share information about what we're doing in research, but really for people in the public, it's often very difficult to access what's going on in research, and most scientists have a very difficult time trying to communicate what they're doing even. So we're trying to make that more simple. So we've created a web portal, apcari.ca, that will hopefully facilitate that communication. So we have information on prostate cancer, but the most important information in here is the information on what the group is doing. So what clinical trials are going on in Alberta, what research we're doing, how to get involved in clinical studies, and we haven't launched it yet, so like I said, we did the soft launch of the site a few weeks ago. We're going to optimize it, and then we're going to launch a blog as well. So we're going to blog on sort of the updates that the team is doing, updates on recruitment in the study, milestones that we're achieving, and really share in real time what the group is doing, with obviously our most important beneficiaries. Cool. So I'll stop there. I'm just the figurehead of a very large, passionate group of very talented scientists and other people. My lab in Edmonton has great young scientists and great young minds. The group itself is very energized and dynamic, and we work with a large international network of partners as well. So thank you so much for your attention. Anybody have any questions? Yeah?
I have a couple. About that tumor glue, you said that it stops cells from moving.
Yeah.
It contains something. What happens at that point? Has it been discovered whether the cells actually die or they just sit there?
So yeah, so they don't die. So but then they are susceptible to treatments that you can come on afterwards. So this particular pathway that we're hitting basically sticks them. So it doesn't kill them, but it leaves them there. So obviously, like, as I mentioned, surgery is a way to get rid of them. So we envision that this treatment wouldn't be used as a single agent, but we use in combination with other drugs that would kill the cells. Oh, I'm sorry. So the question was, this tumor glue drug, does it kill the cells?
Is this glue effect, are you finding it works with any other place in cancer, or is it just exclusively prostate?
Yeah, so the initial experiments we did were in head and neck cancer. So we've now tested in about 7 different cancers. Basically, any cancer that has the protein target on it will be affected in the same way. So we've seen it with 7 or 8 different cancers now.
Do you have a copy of your presentation?
Absolutely. I'd be happy to share it. Yeah.
If the cancer
Yeah, I mean, that's a good question. I get that question all the time. Oh, sorry. And the question is, so, oh, okay. Okay, so the question is that it's sort of the cat's out of the bag. Once a cancer has spread, is it too late for this treatment? So we don't know because we haven't had a treatment like this before. But my feeling is that yes, it will definitely make a difference. So there are many studies that show that the initial spread is only the very first step. So even so once a cancer spreads to a distant part of the body, it can then respread. And it actually can go back to the original tumor. So typically, cancer cells that are moving throughout the body will home into certain sites that the cancer cells themselves improve. So the earlier you can stop the metastatic spread, the quicker you can limit the damage.
Any other questions? There, yep.
Has there been any studies about hypothermia treatments like they do in Germany? Have you guys looked at doing that kind of research?
No, we're not working on hypothermia.
Why is that?
Because we're focused on metastasis. But so I'll say though, I mean, if there's an interest from the physician groups in Alberta to do a trial and look at hypothermia, then that's something that would come up in our meetings and that we would definitely look at.
More?
I'll let Eric do it.
Could this tumor glue help in other cancers than just prostate cancer?
Yes, so we believe it has. So certainly in the animal models we've looked at 7 or 8 different cancers now, and certainly it seems to have that effect on all metastatic cancers we've looked at.
Okay, thanks.
All right. How are we doing for time? Probably maybe one more question here.
I'll be quick. I'm a bladder cancer survivor, so I'd just like to know, is there any plan to try it on bladder cancer?
Yes. Yeah, we actually have. So bladder cancer is one of the, so Eric has an interest in, and our group has an interest in bladder cancer as well. And we have done those studies with bladder cancer, and it does have an effect as well. And we think the test will also be useful for bladder cancer as well.
Hi there. I have one question. I think it's an important one for, as a group of cancer survivors and their families, what can we do to support the work that you're doing? I mean, obviously, money drives things, but is there something that we can do to move this forward? And is it education? Is it spreading the word? What is it?
So absolutely. So feedback on the website would be fantastic because we're basic scientists and several physicians put the website together. We tried to appreciate what people are looking for. It's really important to me with the blog to be able to share things, what we're doing, and get feedback. More education about the clinical study that we're running would be fantastic. So if you have any friends or colleagues that may be suspected for cancer, let them know that we're doing a clinical study and that they can contribute. And the quicker we enroll the patients that we need to answer those questions, the quicker we can answer the questions.
I'll comment on that as well. I mean, I think you need to do everything. The education, the support. This is a huge initiative, the AppCarry initiative, and I think we can do it better than anybody else. Certainly in North America, we have this focused healthcare system where we're looking after 3.7 million people, and we can track their data. And we've got a pretty good team of clinicians. I might be biased there, and basic scientists all focused on this task. So it's a monumental task, and we certainly need your help in all those areas, keeping the momentum going and financially as well. All right, last question here.
Do you do any tests as far as ultrasound is concerned on prostate cancer?
So as a basic scientist, you probably want to keep me away from your ultrasound. But Eric actually has run a trial in ultrasound. So like I said, so the group is, our goal is to facilitate research and bring it to the clinic. So certainly there are trials with new ultrasound machines that the group is doing, and obviously we're doing whatever we can to facilitate that. I don't know if you want to mention that trial.
Sure, yeah, we're looking at a new ultrasound machine. It's a high-res ultrasound that may be able to visualize a cancer, and if that actually bears out to be true, that will be a game changer for sure. But we're still analyzing the data, so I got nothing to tell you other than it is ongoing. And one last comment about the bladder cancer thing. I think these initiatives were set up for prostate cancer, but once you have the structure, the infrastructure, and the labs and the clinicians, I think this can be carried onto other malignancies, bladder, kidney, all of these. So we're working on those as well. All right. Thank you very much, John.